Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 26, 2026, just 2 days ago. It introduces LingBot-VLA, a robotic foundation model trained on a massive set of 20,000 hours of real-world data, which achieves training speeds up to nearly 3 times faster than existing codebases. The paper is titled, A Pragmatic VLA Foundation Model, and as we'll see shortly, the sheer scale of the data and the efficiency of the infrastructure offer a really promising path for general-purpose robot learning. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, you can download the 4 billion parameter LingBot-VLA weights. Both standard and depth versions are available with usage examples for dual-arm robot control. Figure 1 captures this entire pipeline, illustrating the flow from raw data to deployed skills. On the left, the process begins with large-scale data collection, where dual-arm robot footage undergoes automatic annotation and human refinement to create high-quality training examples. Moving to the center, the architecture features a unified action space, merging an understanding expert for perception with an action expert that handles continuous control. The charts on the right then highlight the payoff, where LingBot-VLA significantly outperforms competitors like Pi 0.5 on real-world benchmarks. Finally, the bottom panels showcase these capabilities in action, with robots performing delicate tasks like peeling a lemon or folding towels. Figure 2 visualizes the sheer scale and variety of this data collection effort. The top banner represents the massive pre-training dataset, which spans about 20,000 hours of real-world interaction. Below that, we see the 9 distinct robot embodiments used to gather this footage. These range from humanoid designs like the Leju Quavo 4 Pro and Qinglong on the left, to wield dual-arm platforms like the Agilbot G1 and Agile X in the center. By training across such diverse hardware, the model learns robust skills that aren't tied to just one specific machine. So following that extensive data collection, Table 1 presents the real-world performance on the GM100 benchmark. Here, the authors compare LingBot-VLA against state-of-the-art models like Wall OSS, Groot N1.6, and Pi 0.5. The columns track both success rate and progress score across the 3 robot platforms we just saw. Looking at the average row at the bottom, the results are clear. The depth-enabled version of LingBot secures the top spot with a success rate of roughly 17%, noticeably outperforming the closest competitor, Pi 0.5. Well, beyond just task success rates, Figure 4 highlights the efficiency of the training infrastructure. These 2 charts map out the training throughput, measured in samples per second, as the system scales from 8 to 256 GPUs. On the left, using the QN 2.5 base model, the green line for LingBot tracks the dashed gray line of perfect linear scaling almost exactly, leaving the blue star versus LA baseline far behind. Similarly, on the right with the PolyGemma model, LingBot again dominates, maintaining near linear growth, while competitors like OpenPI and Dexbotic Plateau significantly lower. Alright, having confirmed the training efficiency, Figure 5 investigates the impact of data scale. Here, we see the progress rate on the left and success rate on the right plotted against the volume of pre-training data, which ranges from 3,000 up to 20,000 hours. The bold red line marks the average performance across all platforms, and it climbs steadily without plateauing. Crucially, the dashed lines for specific robots, such as the Agilbot G1 and Galaxia R1 Pro, mirror this growth, proving that the model generalizes better as it sees more real-world examples. Wrapping up, 2 takeaways stand out. Massive real-world data drives better generalization, and efficient infrastructure is key to unlocking it. This work strongly suggests that robotic learning is following the same scaling trajectory as large language models. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.